Hello and welcome to this tutorial on performing a side channel power analysis with the CW305 Arctix FPGA board. So to begin, we'll use this hardware setup here where we have a laptop, we have the 305 board, and we're going to use a Chip Whisperer Lite as the capture hardware. Now we just plug in the CW305 and Chip Whisperer Lite over USB, and we then connect the two using a SMA cable. So this is on the amplified output on the FPGA board. And this power measurement connects to the input on the Chip Whisperer Lite, the measure input. Again, if you're using the Chip Whisperer Pro or others, it has the same type of measure input there. We also have this 20-pin ribbon cable, so this will be used for clock and trigger information. Data will go over the USB to the Arctix FPGA board. It doesn't use the serial protocol like other targets do. So yeah, with that setup in mind, we can fire on over to the software. So on the software side, we basically have the 305 as a supported target board. But actually this whole setup, what we can do is we can just run this script here, 305 Arctix target with Chip Whisperer Lite. So this should be in any recent release of the Chip Whisperer software. When it connects, hopefully what you should see is it detects both the FPGA and the Chip Whisperer Lite, as you can see there. And if it doesn't, so you will need drivers for Windows. So you can find those on the release page if it's not finding the board. What you will need to do though is you will need to tell it what bitstream you want to program in the FPGA. So there's a bitstream file option here on the target setting page. And Chip Whisperer has, so there's an AES example, but there's some pre-built bit streams for it. So there's actually another tutorial that goes through how you can build these bit streams. If you just want to follow along though, it's in the Chip Whisperer repository. So you go down basically to the main Chip Whisperer. You can download this from GitHub too. There's a hardware subfolder in there. There's victims. So this is all the target boards. There's a 305 Arctix target. So that's this board, FPGA subdirectory, Vivido examples, AES-128 Verilog, not quite done yet. The .runs folder now has the two different versions of the bit stream. So this board I'm using has the 35T size FPGA. Double check you have the right size FPGA. When you program it, if you don't, it just won't program properly. You won't get this FPGA config OK message at the bottom. And you'll also see the board has this FPGA done LED. So it's on when it's unprogrammed. This is an artifact of how the output pin works in the FPGA. When it's programmed, the light will go off, and you may see some blinking lights right away, or you should at least see the red light, which indicates the USB clock is running. To get the green one blinking, it has to have the AES clock has to be set correctly. So you have to double check J1 is set to the left there, and K16 is set to the right. So when you set it that way, it's going to get the clock from the onboard PLL and send it over the 20-pin cable. We can double check this in the software, and we double check this by going down to the ADC Clock section here. And there's this X clock signal, and basically this frequency counter should be the frequency, the 10 megahertz from the board. And we can double check that the ADC is running at 40 megahertz. You may have to hit that reset ADC clock button there if it's not locked, if you don't have the right frequency. But yeah, if you hit capture 1, you should get a few power traces like this. You'll also see the power traces. You can open the encryption monitor just to see the encryptions are running correctly inside the FPGA. So on the right side, you see the waveform there. We might adjust it to get a sort of nicer looking waveform. The actual AES is happening just in those large spikes that are within the first 60 sample points. So that's actually in each round, we're seeing one of the spikes from the AES algorithm. So there I found sort of a nice setting for the gain. You can play around a little bit with the phase shift. Sometimes it matters, sometimes it doesn't. You can also play around with the frequency it's running at. So there I've increased the frequency, and you can see there's sort of a bigger dip in the static power consumption. But anyway, so to continue with the tutorial, I set the frequency back. And I'm now just going to capture about 5,000 traces. So I'll set a project. I'll save the project first. So there I've saved the project. I'm going to set it to save about 5,000 traces. And I've chosen to do this in two segments. So it's going to save two segments of 25,000 each. That way I can abort early if I don't want to wait the whole time. You may actually want to make it a few, like 10 sets instead, like I've done here. The other thing you can do is you might be able to speed up capture. You can turn off drawing the waveform here in the results tab. So you see if I can set that to none, or I can set it to the ADC channel. When it's set to none, it just doesn't redraw. So you may want it to redraw just so you can monitor the capture as it's going. Anyway, so using sort of TV cooking show, what we've got here is we've done the capture, we've saved it, and then we're going to open the Chip Whisperer Analyzer. Inside of the Chip Whisperer Analyzer, what we do is we simply open that project that I saved, and you should see all of those traces here. Then what we're able to do is we're able to actually try applying a CPA attack. So one of the things with the CPA is what's the sort of leakage model. So there's a whole bunch of them, and the written tutorial goes through this. But basically, we have this Hamming distance on the AES last round state. And we're also going to tell it to use a shorter point range, 0 to 60 points, and a smaller reporting, or a larger reporting interval that will say every 250 traces, tell us what the current status is. And we just do this because it's going to take more traces to break this hardware AES, and it runs a little faster. So you'll start to see pretty quickly the correct bytes filtering up to the top. So the correct bytes are highlighted in red. You'll notice this is the last round key, so don't get hung up on that. What's getting highlighted here, this D014, etc., is not the encryption key for the first round. Was the standard 2B7E blah blah blah. The software knows you're using the last round key, so it's highlighting a different key than you might expect. You can roll this back to the first round key if you want, but don't get hung up on that. So anyway, you should see this pretty quickly. Appears to be breaking the AES on the hardware implementation. And again, this is using the model of we're leaking information between successive states of the AES, the successive states that are being stored in AES, and I'm looking in particular at the very last round that it's operating on. And in the tutorial, you can see there's a little more detail on that. Now, the interesting thing here, I can plot the location of the leakage, so where are we seeing these high correlation spikes, and we can see right around what the sample number that is. Now, we can pop over to the trace view itself, so the actual power trace, and we can go ahead and sort of see what that same point is, and you see it's right around this big spike here. So we actually know this is the moment in time where we have this Hamming distance leakage. So this is the moment in time probably where the last round of the AES state is getting written to the internal register. So that's a quick example of performing a side channel power analysis against an FPGA target, in particular the CW305. Hope you have fun.